Hello everyone, my name is Matthew Deardorff, and today we're going to be taking a look at using the Earth mover's distance as a similarity measure for linear order statistics and fuzzy integrals. So the first thing we need to do is orient ourselves as to where we are in the world of information fusion and why we care about similarity measures in the first place. So we have this task of aggregation where we are trying to take disparate sources of information, maybe those are sensors or algorithms or experts, and we would like to combine their evidence into a single source that is somehow more reliable than any of the sources by themselves. And there are many ways to formulate this problem, of course. We're going to be taking a look at fuzzy integrals specifically, but you could do something like a neural net or something a bit more complicated. And within the world of fuzzy integrals, as we're going to show here in a sec, we can break this down even farther into linear order statistics and order-weighted averages. And these little guys are these cute little operators here. They are simply ways of aggregating data with a very small number of variables, but we can also consider fuzzy integrals as being larger operators. They are more complicated, they have more parameters, but they're capable of doing a bit more work in the world of aggregation. And so the question here is, how similar are any two of these operators? We can compare on a linear order statistic level how similar these two are, but we can also get a bit more fancy and try to compare fuzzy integrals. How similar are they? And even more so, we can try to cross the streams a bit and compare an order-weighted average or a linear order statistic to an integral itself to get the similarity measurements. And so again, why do we care about similarity? Well, there's a few reasons. One, of course, is always just academic curiosity. We noticed this issue that we had in another paper, and we wanted to address the similarity measure that was causing some problems. But there are, we're always just curious about using our math to extend what we've already done. Got another paper on contextual fusion, which is about how do you know which classifier to use? How do you know what context you're in, what environment you're in? Can you try to select what expert is appropriate at the given time? That all involved using similarity to determine, to make those choices. And then, as we're going to talk about in this paper, we can also do operator discovery, where given an integral, can we tell, well, what was learned? How many operators exist in it? Is the integral too complex of a machine or not complex enough? And can we explain all of this to the user? And there's many reasons more, but this is what we're going to stick with for now. So all of this is going to be built off of the Choquet integral. So first things first, let's give a description of the integral and how it works. So the integral is going to be a function on two inputs. One is the input from the sensors themselves. So again, this would be a readout from a thermometer or from a camera or whatever. And g here is a set-valued function, which is called a fuzzy measure. And a fuzzy measure has a few different properties. One are its boundary conditions. So g of the empty set is going to be 0, and g of the universal set is going to be 1. This will turn it into a averaging operator that is bounded between the smallest and largest values that were observed. And then we've also got monotonicity constraints here, saying that if we've got two subsets, A and B, and that A is subset equal to B, then g of A is going to be less than or equal to g of B. Now, the actual equation for the Choquet integral is given right here, and as you can see, it is essentially a weighted sum of differences between these g values here. And pi is going to represent a sort on the inputs, such that h pi of 1 is greater than h pi of 2, and we're going to establish that g of a of pi of 0 is 0, and that a of pi of j is going to represent the first j sources when sorted according to pi. A lot of times an easier way to understand the Choquet integral is through these Hassi diagrams, which visualize the underlying fuzzy measure on the integral. And so as we can see here, the diagram consists of nodes that are connected with these monotonicity constraints. And in order to execute an integral, you will start on the bottom layer of the diagram here and work your way up to the top using any unique path up this diagram. And the unique paths are all going to represent different fusion strategies, different linear order statistics, meaning that each unique path is a unique way of combining the data. So here's a little numerical example down here. Here are our inputs, and we can do a sort of a pessimistic fusion where we're averaging the two lower values. We can do an optimistic fusion where we're averaging the two higher values. And it should be pointed out that we can construct all the, good old max, min, average operators using these fuzzy measures. So to move on to the decomposition, as noted before, an integral can be broken down into a set of linear order statistics. So the way we're going to be doing that is by enumerating through all the different paths up this Hassi diagram. So for example, this red path here is going to correspond to one LOS. A separate path, which does share some values here, share some weights, is going to result in a new LOS. And we'll end up enumerating through all these different paths until for n inputs we get n factorial different operators. Now what we would like to do with these operators once we've sort of unrolled them is we'd like to cluster them and determine what structure, if any, exists within the integral. So is there only one operator maybe, or is every single walk actually unique? But in order to cluster, we need a similarity measure. So that is where this paper comes in. So the first thing we tried when doing this decomposition technique was what we thought was a reasonable first step, which is using like a Euclidean distance or an L2 norm. Because as it turns out, these LOSs are already in a form that kind of lend themselves to an element-to-element comparison. So something like a Euclidean distance makes a lot of sense as far as how you would implement it. But what we found out pretty quickly was that this was actually kind of deceptively wrong. And there are examples where it does work, but there are more examples where it does not. And so we're going to take a look at some of those failure cases. And before we move on, it can be noted that while Euclidean distance is obviously a distance measure, if you subtract the distance from the maximum possible distance, then you can convert that into a similarity measure. So here are some failure cases as to why the Euclidean distance doesn't work for LOSs. We've got the max, min, median, and mean here, and we can represent those just with the coefficients on this equation here. And so if we just do the Euclidean distance on some of these values, we get the similarity between max and min is 0. So that seems reasonable. A maximum and a minimum are probably as different as you can be for a linear order statistic. But the similarity between the max and the median is also 0, and that seems a little weird. You would imagine that the median is somehow going to be a bit more closer to the max than the min is, but this is not reflected in the Euclidean distance. And similarly, we can see that the similarity between the max and the mean is about 0.423, so that seems reasonable. A maximum is somehow similar to the mean. It's closer than min, but what we see here is that the median is also 0.423 similar to the mean. And that seems really weird. Even though the median and the mean are not exactly the same thing, obviously, you would imagine that typically the median is going to give you, closer values to the mean than the max will, but the similarity measure doesn't seem to describe that. And we get the similarity between the max and itself as 1. So all good there. And so the important thing to notice here is that the Euclidean distance, which is like a bin-to-bin and element-to-element comparison, it's going to disregard the sort order, which, if you recall, for the Stochastic integral, we sort all of our data as one of our steps, meaning that the x pi 1 here is always going to be the greatest value, and the Euclidean distance disregards that sort order. So we want some sort of smarter similarity measure that takes into account the sort order. So the solution to this is we're going to use the earth-mover's distance. It, as it turns out, is a lot more appropriate and works in all the cases where the Euclidean distance does not. So if we kind of reframe how we're thinking about this problem here, we've got the max, min, median, and mean depicted as histograms, where you can also think of them as like a pile of dirt. And what the earth-mover's distance is going to say is, well, how much work does it take to move this dirt over here if we're going to compare the max to the min? And so if you take a lot of dirt and move it far, that's going to be the greatest possible distance. Or if you only take, if you take this dirt and move it only a little bit, that's less work. So as mentioned before, that is now using the sort order of the data as part of its similarity measure. So to actually calculate the earth mover's distance, we're not going to go through all this math because it's not too important. There are libraries for how to do this, and it's well documented how to compute the earth mover's distance. But we are minimizing the flow times the distance for each pair of indices here, for each bin. And again, we can turn this into a similarity measure by taking the maximum value of the earth mover's distance and subtracting it from the actual observed value to turn it into a similarity measure. And the reason this works is because we were able to define this ground distance matrix D, where that defines the distance between any two bins. So this matrix here, for example, would be for n equals 4 inputs, saying that bin 1 is, on top of itself. There's no distance there, but bin 2 is 1 unit away, bin 3 is 2 units away, and bin 4 is 3 units away, and there's no wrapping around here on the edges, of course. And by encoding the ground distance matrix this way, you end up getting that the semantic understanding that we had from before, where max and min are as far apart as can be, but maybe median and max are closer together or whatever. And so now when we use the earth mover's distance instead of the Euclidean distance, we get these values, and these ones end up being a lot closer to what we would expect to see, what we would want to see. So max and min are as different as can be. They're not similar at all. Great. But max and median do have some similarity, so that's better than the Euclidean distance. And the same with max and mean. They are also somewhat similar. Good. And then what we'd also like to see here is that the median and the mean are actually very similar. And again, that's how we imagine these operators. They are more similar than any other operators here. And we still have our idempotency. Max and max are similar to each other, so all good there. So now that I've hopefully kind of convinced you as to why the Euclidean distance doesn't work, but the earth mover's distance does, we can try to extend this to work on more than just linear order statistics, but on the entire Choquet integral itself. So the way we're going to do that is borrowing from our decomposition procedure. We are going to enumerate through all n factorial different linear order statistics that exist within a Choquet integral. And we're going to use the earth mover's distance on each LOS pair and do a sum on that, and then divide by the total number of linear order statistics to get the average distance between the Choquet integrals. So this formula is trying to describe if you were to select any random linear order statistic, any random fusion strategy in this integral, how far would it be from the same fusion strategy in this other integral. And another extension we can do is, because we typically learn these integrals from data, we actually have statistics about which data, which sorts were seen in the training data and what sorts were not. And based on what sorts we've seen, we can we're kind of more willing to believe those values. For example, if we never saw a particular sort in training data, then we might expect to never see that sort in real life either. So if that's the case, we can use those training data statistics to weight our measure based on the frequencies of those particular sorts. So if a specific integral is dominated by one sort, so maybe we always take a single path in the integral or in the diagram, that is obviously the most important linear order statistic to compare. So we're going to heavily weight that one while not weighting all the paths that we didn't take. So to return to the decomposition procedure described at the start, we can now do that from start to finish with a fuzzy measure using the earth mover's distance. And so here's our 4-input integral. We're going to enumerate through all the different paths and compare the LOSs using the earth mover's distance. That will generate something that looks like this. This is a dissimilarity matrix where the darker colors represent pairs that are more similar to each other, and the lighter colors represent pairs that are dissimilar to each other. And using something called the VAT algorithm, we can reorder these such that we get these nice clusters where everything up in here is basically one operator and everything down here are all operators that look very similar. So we can try to color code these, give these actual designations, and try to visualize where in the integrals these exist using these color-coded Hassi diagrams. where each node is a pie graph representing the kind of LOS and the amount of LOSs that pass through that node based on the color designation here. So the top and bottom nodes, since every LOS visits these nodes, we can see that a fourth of the total LOSs belong to the orange cluster and the rest belong to the light blue one. And if we look at this node up here, since it's the only node here that actually has a 1 besides the top node, we can see that any LOS that visits this node is guaranteed to belong to the orange cluster. And we can actually do some aggregation here to see, what are these operators that live in these clusters. And we can see that cluster 1, operator 1, is this 0, 0, 1, 0, so basically like a soft min. And the next one is a hard min, 0, 0, 0, 1. And so while this was a synthetic example, we did do this on multiple real-world training sets, but I'm running out of time, so here's what this looks like. We end up using the AID remote data set. We can either try to cluster it into like 4 different operators, which the results are right here, or we can try to oversimplify it to only get 2 operators, these 2. In conclusion, we've been looking at how you understand Choquet integrals and what the underlying structure looks like. In order to do that, we needed a distance measure, and it turns out we can't make assumptions about what distance measure we should use. We should really consider that carefully. By using the earth mover's distance, we're able to encode a ground distance matrix that is going to reflect the sort order imposed by the Choquet integral, which ends up making our similarity measure based on the earth mover's distance more semantically pleasing compared to what we would expect from those kinds of operators. By decomposing the Choquet integral into its components parts, we can kind of simplify the problem and compare linear order statistics on a one-to-one basis, and then build that up to compare the entire Choquet integral. And then finally, of course, we always try to visualize what was learned by communicating our results to the user. It always is going to lead to, or hopefully is going to lead to, better utilization and better understanding of what our systems are actually doing. And the next steps we'd like to do as future work is there's plenty to do in the world of Choquet integrals. Specifically, we're looking at like variable imputation and what to do when data is missing. So as mentioned before, when we train these from data, if a certain sort is not in the training data, that is kind of like an untrusted path, an untrusted set of variables. So how do we better learn those variables if we're missing the data is a pretty difficult problem. But that's all I've got for now. Thank you for attending my talk, and I will now be around to answer any questions that you guys may have.